In networking, not every message arrives. Some messages simply disappear. This is called message loss. Message loss is one of the most fundamental network failures. It defines the limits of reliability. Networks do not promise delivery. They attempt delivery. So what is message loss? Message loss occurs when a message sent by a sender never reaches its intended receiver. No acknowledgement is returned. No error is guaranteed. From the sender's point of view, the message vanishes. Message loss is not rare. It is expected behavior in real networks. To understand message loss, we must understand failure. Let's start with how message loss happens. One common cause is congestion. When network buffers fill up, packets are dropped. Routers cannot store messages indefinitely. When capacity is exceeded, loss is the result. Hardware failures also cause message loss. A failing router, switch, or network interface can silently discard messages. Link failures are another cause. A cable disconnects. A wireless signal fades. Message loss can also occur due to software errors. Bugs in network stacks can drop messages unexpectedly. Security mechanisms can intentionally cause message loss. Firewalls may discard messages that violate policy. Rate limiters may drop excess traffic. In all cases, the outcome is the same. The message does not arrive. Now let's talk about why message loss matters. Message loss breaks assumptions. If a system assumes delivery, loss causes failure. Commands may never execute. Requests may never be processed. State updates may never be applied. Message loss forces systems to confront uncertainty. In unreliable networks, silence is ambiguous. Did the message arrive? Was it lost? Is the receiver slow? Message loss cannot be directly observed. It can only be inferred. This ambiguity shapes network behavior. Let's examine the defining characteristics of message loss. First, message loss is invisible. The network does not always report it. Second, message loss is timing dependent. A delayed message looks exactly like a lost one. Third, message loss is asymmetric. One direction may lose messages while the other works normally. Fourth, message loss is workload sensitive. Under high load, loss increases dramatically. Fifth, message loss compounds failure. One lost message often triggers retries. Retries increase load. Increased load causes more loss. This feedback loop can destabilize systems. Message loss directly influences protocol design. Reliable protocols exist because messages can be lost. Acknowledgements exist to detect loss. Retries exist to compensate for loss. Timeouts exist because loss is indistinguishable from delay. Message loss also shifts responsibility upward. The network cannot guarantee delivery. Applications must decide how to respond. Some systems tolerate loss. Streaming media may skip lost data. Other systems cannot. Financial systems treat loss as critical. Message loss also affects observability. Metrics may undercount events. Logs may show gaps. Message loss has security implications. Lost messages can hide attacks. Dropped alerts can delay detection. Message loss is not a mistake in networking. It is a design constraint. Networks trade certainty for scalability. Message loss is the cost of that trade. Robust systems expect loss. Fragile systems assume delivery. Messages carry intent. Networks may drop them. Systems must decide what that means. When you understand message loss, you understand retries, timeouts, backoff, and failure handling. Message loss defines the boundary between best effort and reliability. That is message loss,